Hey everyone, we are going to be taking a look at chapter 12, which talks about rules of general probability. And to begin, just a really quick review of some of the things that we had looked at before. We talked about one of the first rules, that whenever you're talking about the probability of an event occurring, and we'll just call the event A, so the probability of A occurring, we said that number is somewhere between 0 and 1. All right, where 0 is the event never occurs, and 1 is really 100%, the event always occurs. So we also talked about something called the sample space. So the probability of the sample space always adds up to 100%, or just 1. So when we're looking at a few things, we have to realize how we can kind of model these things with a Venn diagram. So here is an example of a Venn diagram where this represents the entire sample space. All right, so let's imagine that we are talking about a deck of cards. Okay, in a deck of cards, I would have 50% of the cards would be red, and 50% of the cards would be black, and none of the cards would be outside of either of those. So when I'm looking at this Venn diagram, this sample space is all 52 cards. All right, 26 of those cards are here, 26 of the cards are here, and 0 cards are out here. So that's where 26 out of 52 is why we get the 1/2. The same thing over here. There's nothing left over. So we look at this and say these have to add up to be 1. That's everything. All right, so the 100% chance that we have in our sample space. Now, one thing to notice about these events is we say that these two events are disjoint. You can tell when two events are disjoint because they don't overlap. It is not possible, it's impossible for you to draw a card that is red and black. All right, when we're using a standard deck of cards, half of them are red, half of them are black, but there isn't a card in there that's both. All right, so they're disjoint. There's no overlap of these two ideas. However, if I use the same idea with a deck of cards and say, here is, I want to find out the probability of getting a red card or a king. All right, normally we would have said in this last example, the probability of getting a red card or a black card, because they're disjoint, is we just add them together. All right, so if I would have said, oh, I want to find the probability of getting a 5 or a 6, I would have looked at each one of these. I would have said the probability of getting a 5 is there's 4 of them out of 52. The probability of getting a 6 is 4 out of 52 cards. The probability of getting 5 or 6 is adding these things together and being able to say, okay, it's 8 out of 52. I can throw that into decimal form. Looks like it's 15%. That's the probability of getting a 5 or a 6. All right, when I'm taking a look at it. Those two cards were disjoint. If I would have had them put on here, here's my 5s, here's my 6s, they don't overlap. That's not the case with a red or a king. Here are all my red cards. Here are all my kings. Okay, I know that there are 26 red cards. I know that there are 4 kings, but I also know that there are 2 red kings. All right, so I'm just going to put the numbers in here. Here's my 2 red kings, the hearts and the diamonds. Here's the rest of my kings, and here's the rest of my cards. So if I look at this all together, I'll see here's my 26 red cards. All this circle is my 26 red cards. Here's my 4 kings. Here are my red and king. So my red kings. Now, normally we would do these with the probabilities. So 24 out of 52 is 0.46. 2 out of 52 is 0.038. And 0.038. But I'm just going to round this off and say 0.04 and 0.04, just so that we have something a little bit easier to work with. But that shows me, when I put all these together, here is my 50% of the cards are red. All over here I have 0.08. That's how many of my cards are red kings. All right. When I want to find the probability that you have a red or a king, I am going to basically look at this and say, well, red or a king means I have all my red cards plus all my kings, but I'm only going to count the kings that are red once. All right. So really I have this. Probability of red plus probability of king minus the probability of a red king. All right, red and king. So the probability of a red card, 26 out of 52. Probability of a king, 4 out of 52. Probability of red and king, 2 out of 52. When I add these together and subtract this, I end up with 28 out of 52. And notice those are the numbers I have here. 24 plus 2 plus 2. That's the probability of getting a red or a king. Okay, so you have to adjust some things because of that overlap, right? Noticing that you go through here. Now, one of the things we should note is when you have this idea of probability of A and B, there are two types of events that you can have it. If these events are independent, then the probability of A and B is found by just taking the probability of A times the probability of B. All right. Independent means that one result has absolutely no influence on the other result. So for our example here, if we take a look at this, the probability of getting a red card is 0.5. Probability of getting a red card or a king, and I'll just round it off, or excuse me, not a red card, but a king. There's 4 kings, 0.08. If I multiply these two things together, I get 0.04. That is the and. That's because these are independent events. All right. Drawing a card that is red has nothing to do with drawing a card that's a king, even though some of them are both. Now, that's not always the case. And let's take a look at putting a Venn diagram together that matches one of the things in the book here, because they're not always independent. In the book, they have, for one of the examples, they have domestic cars, trucks, and then domestic trucks. I don't know why I'm spelling it wrong, but that's fine. So I'm just going to make this simpler, though. I'm just going to call it, here's D, here's T, and here is domestic truck is D and T. All right, and they basically have this example where they say 77% of all vehicles sold to individuals were domestic. So 77% are domestic. 44 or 52% were trucks, and 44% were domestic trucks. So if I'm looking at this, where I always start is the idea that I look at where is that overlap occurring. The overlap is occurring between domestic and truck. So here is 0.44. These are my domestic trucks. 44% are domestic trucks. Now 52% are trucks, so that only leaves me with 0.08 left. 77% were domestic. Well, this whole circle is 0.77. I only have 0.33 left, because if I add those two together, I get my 0.77. One of the things that we noticed in class, and I should have caught this right away, is that if I were to have asked the probability of domestic and truck, and I look at this and say, well, that's probability of domestic times probability of truck, I would end up with 0.77 times 0.52. And if I put those together, we notice that it was wrong. So 0.77 times 0.52 is 0.4004. That is not, it's not even really close. That's 40%. Our answer is 44%. That's because these are not independent. What I mean by that is I believe that there is a relationship. Whether or not a car or vehicle was made in the United States or intended to be sold. Most of the vehicles made in the United States are intended to be sold in the United States. And that's going to be different than the vehicles that are not made in the United States. I think because of our geography, the types of jobs and things, that a lot of the trucks, we have a lot of people that drive trucks in the United States. I don't think that's the case in a lot of different countries, sometimes because of the logistics of driving a truck. So they don't make as many of them. That really is the idea, that being domestic and truck are not independent. There's a greater likelihood that you're going to make a truck in the United States than there is making a truck in a different country. But when we take a look at all of these things, I have 77% are domestic, 52% are trucks. When I put all of these together, 0.33 plus 0.44 plus 0.08, once I have the overlap figured out, that ends up being 0.85. 85% are domestic or trucks. So 85%. That means out here, if you are not domestic or not a truck, or I should just say not D or T, you are 15% of everything. The only thing that's not domestic is imports. The only thing that's not a truck, that's cars. So these are imported cars. That is the parts, the imported cars are here. Again, the fact that this 0.4 doesn't get multiplied together by these two things shows that this is not an independent event. So as you're going through here, you probably will notice this in the example that you have in 12.5. They just give you these three things. Here's the probability of A, the probability of B, and the probability of A and B. A is greater than 25 years old. B is local. Local people 25 years old. These are all are taking community college or distance education. Here is 70%. This was 25%. And this was 0.5%. You can check this right away. Probability of A times the probability of B. That's 0.7 times 0.25. It's not going to be 0.05. All right, notice that's because these are not independent. All right, that's what happens. That's what that means. So we have to go with the figures that they have figured out by putting together that Venn diagram. That's really what your first step is, saying like, okay, where do these numbers fit? Where does the 0.05 go? How do I get to the 0.7 and 0.25? Where do they put on in here? They're not independent because I imagine where you live in relation to a college is affected by your age. I'm guessing that most people that are older than 25 and don't want to be up all night because of all the crazy college parties, they're going to live further away from the campus. It also means that people that are taking online education are probably doing so because they're not local. So these two things are kind of interdependent. They're not independent. But anyway, that's what we are working on in 12.5. And so really we have a couple of things. We have the general rule of probability. When we say A or B, we're doing probability of A plus the probability of B minus the probability of A and B. And keep in mind that you could use this for anything. If there is no overlap like red and black, this would be 0. But this is for any of them. If you did it like this and just had this first part, this only works in disjoint events. All right, this one would work in either of them. And remember, the probability of A and B is just found by multiplying. But again, that multiplication assumes that A and B are independent. All right. Otherwise, the probability it can be affected. You just have to do the actual measurements. But mathematically, if they're independent, we can just multiply them together to be able to figure out all of these things. So those are the three main ones that we have in the first part of chapter 12.